So welcome back to the mathematics class, and we were talking about quadrilaterals. So let us continue from where we had stopped. In our last class we had covered the topics parallelogram and another condition for a quadrilateral to be a parallelogram. So in this class we will cover the last topic, which is the midpoint theorem. So let us start off straight away. Now let us learn what is actually the midpoint theorem. So before we actually move into the theorem or the statement, let us see what it is actually based upon. So let us consider the triangle ABC. Let us consider this triangle, and what we have done, we have drawn the midpoints of sides AB and AC. You can see the corresponding midpoints of the sides are D and E, right? And what we do, we join D and E, and by joining D and E you can see we have got two straight lines, which is BC and DE. We have got two straight lines, and actually the entire midpoint theorem is based upon these two straight lines, or the characteristics of the figure when we draw a straight line joining the midpoints of the two opposite sides. Now by joining this you will actually find that DE, the line joining the midpoints, is actually parallel to the base, right, or to the third side. The two sides we have drawn the midpoints and joined them, and that line should be parallel to the third side. This is what actually the midpoint theorem is based upon. And why it is called that? Because we are joining the midpoints of two sides. So let us see the statement. The theorem states the line segment joining the midpoints of the two sides of a triangle is parallel to the third side. The line joining the midpoints of the two sides, which is the line DE, is parallel to the third side, which is BC, which we have got, right? We have learned that. Now let us show that this theorem is actually correct. And how do we do that? We do certain constructions to make our work easier. So one of our constructions is the ray CX. And how do we draw it? We just don't draw it randomly. We draw CX parallel to AB, and you will see why do we do this. We draw CX parallel to AB, and then what we do, we extend DE to CX. We extend DE to CX, and we get the full line segment DEM, right? So here what is there? AB is parallel to CX, and AD and BD are equal, AE and EC are equal, because D and E are the midpoints, and also you can see we have extended DE to reach here at M. So let us show it. Let us show the theorem. Now let us consider two triangles, two smaller triangles, triangle ADE and triangle CEM. Let us consider these two smaller triangles. And why are we considering it? Because we need to prove that this side is actually we are given that this side is equal to this side, right? AD is equal to BD, and we have to prove DE is parallel to BC, and our aim is to show that BDMC is a parallelogram. And if we can show that BDMC is a parallelogram, obviously DE will be parallel to BC. So let us see how we can show that this is a parallelogram. We have taken the two triangles ADE and triangle CEM, and from this the vertically opposite angles, angle AED and angle CEM, are equal to each other, right? Because they are vertically opposite. And AE equal to EC, right? Because E is the midpoint of AC. This side is equal to this side, and DAE, angle DAE is equal to angle ECM, which is this angle. And why are they equal? AB is parallel to CX, right? And if we take AC as the transversal, you can see this angle and this angle are actually alternate angles. This side is parallel to this side and AC is the transversal, right? So this angle is equal to this angle because they are alternate angles. So we have got three criteria, which are angle, side and angle. So we can say that triangle ADE is actually congruent to triangle ECM, right? Or in the correct order, CME. You should always focus on the order, because when we are putting in the congruency sign, it always means that by the letters we have shown, they overlap onto the letters shown on the other side of the congruency sign, right? And from this you can see A we can overlap it on C, D we can overlap it on M, E we can overlap it on E itself, right? So we should always write congruency of two triangles in the same order as they can overlap onto each other. So triangle ADE is congruent to triangle CME. And by CPCT we get AD is equal to CM, right? AD is equal to CM, or as AD is equal to BD, so BD also must be equal to CM, right? So these two sides we have got as equal. Now can you recall the theorem we had learnt in the last class? If two sides of a quadrilateral are equal and parallel, because BD is parallel to CM, right? If two opposite sides of a quadrilateral are equal and parallel, what is the quadrilateral formed? It is actually a parallelogram, right? BD is parallel to CM, so BDMC, we have proved that it is a parallelogram. And if it is a parallelogram, obviously DM will be parallel to BC, right? The opposite sides will be parallel. DM will be parallel to BC, or a part of DM, which is DE, must be parallel to BC also, right? So you can see DE is parallel to BC, and we have proved this statement, and we have got that the line segment joining the midpoints of the two sides is parallel to the third side, or the side which is not joined. So let us look at one more theorem, or it is rather the converse of what we have seen in the earlier slides. This theorem states the line drawn through the midpoint of one side of the triangle parallel to the third side bisects parallel to the other side bisects the third side. And here let us assume that we are drawing the line from E. We know that AE equal to EC, or we know that E is a midpoint. So if a line segment is drawn from E and parallel to the base, it will hit at the midpoint of the side AB, or the third side. And from the theorem you can see what we initially know is these two are equal, AE equals EC, and we are given DE parallel to BC, right? We are given DE parallel to BC, and we need to show that AD is equal to BD, right? We have to show that AD equals to BE when we have assumed that we know E is the midpoint of one side and we have drawn ED parallel to BC. So let us see how we can prove that this theorem is also correct. and we again do the same construction for making it the question easy. So we are given AE equal to EC as I told you, and DE parallel to BC, right? DE is parallel to BC, and therefore we can say DM is also parallel to BC, because DE is only a part of DM. If one part is parallel, the whole thing must be parallel only, because it is the same straight line. So we have to show that AD equals DB, right? We have to show that AD equals DB, or we have to show D is the midpoint of AB. And from the earlier observations, you can easily find out that triangle ADE is congruent to triangle CME once again, because AB is parallel to CX, right? So these two angles will be equal, or these two angles will be equal, right? And obviously AE equals EC. So you have got two angles and one side. You can also consider the vertically opposite angle with the vertex at E, and you can easily find out that triangle ADE is actually congruent to triangle CME, right? And from there we find out by CPCT AD equals CM, or AD equals CM, right? But BDMC was a parallelogram, right? Because these two sides were parallel. DM and BC were parallel. Also AB and CX by construction were parallel also. The opposite sides were parallel, and in a parallelogram the opposite sides are equal also. If CM measures something, it must be equal to BD also, right? It must be equal to BD also. But we know AD equals CM, right? If AD is equal to CM and CM is equal to BD, obviously AD must be equal to BD, right? And we are writing the same thing. BDMC is a parallelogram as DE parallel to BC and DM is parallel to BC, right? DM is also parallel to BC because DE is parallel to BC, and AB is parallel to CX, and we are considering actually the opposite sides, the AB parallel to CX and DM parallel to BC, right? We are considering the parallel nature of the opposite sides, and we are telling BDMC is a parallelogram. So as I told you, DB must be equal to MC, right? Because these are opposite sides of a parallelogram, so they must be equal. And as MC is equal to AD, BD must be equal to AD also, or we have got these two sides equal, and you can see that means D is actually the midpoint of this side AB, right? We have finally got D is the midpoint of the side AB. So we have proved the theorem that the line drawn through the midpoint of one side of a triangle running parallel to the base or the other side intersects the third side at its midpoint, right? It is just the converse of the midpoint theorem we have talked in the beginning of the class, right? So let us use what we have learnt so far to solve a question. Now here the given figure in the triangle ABC, as you can see here, DEF are respectively the midpoints of side BC, CA and AB, right? All these are the midpoints of the corresponding sides DEF. And you may look at this, actually this is named in a cyclic fashion for easy understanding. Actually for doing more and more questions, you will see that the namings are often in this fashion. A, B, C are named in a anti-clockwise fashion. Also D, E, F are named in anti-clockwise fashion also. You can see the naming of the smaller triangle starts from opposite of vertex A. Opposite of vertex A is D. Then next we go to opposite of vertex B to tell it E, and we name the vertex opposite to C as F. So in this order we have named the triangle and the midpoints of the corresponding sides. And we need to show here that triangle ABC is divided into 4 congruent triangles. And which are the triangles? 1, 2, 3, 4. We have to show that these triangles are actually congruent to each other, right? Or in other words, after joining the midpoints of the triangles, after joining the midpoints of the sides, we get 4 triangles which are exactly alike with each other. So let us start solving it. As D, E, F are the midpoints, we can apply the midpoint theorem. So FE must be parallel to BC, and why? F is the midpoint of side AB, E is the midpoint of side AC, therefore this line must be parallel to this line, right, BC. Also let us look at the line DF and CA. Let us look at DF. Now DF also must be parallel to this side. Why? Because F is the midpoint of AB and D is the midpoint of BC, and we are using the midpoint theorem here. The 2 midpoints are joined. If they are joined, then the line segment joining them will be parallel to the base, right? And also let us consider the remaining side, ED. ED we can tell it is parallel to AB, right? If we see like this, AB is the base and E and D are the midpoints of the corresponding sides, so ED must be parallel to the base AB, right? So from the 3 line segments joining the midpoints, we have got the 3 sets of parallel lines using the midpoint theorem. Therefore we can say that AFDE, which is AFDE, this is a parallelogram. Why? This was parallel to this, right? And also this side was parallel to this side, right? So this was a parallelogram. And similarly BFED, which is BFED, this figure is also a parallelogram, right? And DEFC, which is DFEC, right? DFEC is also a parallelogram in a similar fashion. This side is parallel to this side. Also this is parallel to this, right? And all these things we have got by using a simple theorem called the midpoint theorem. Now let us see how to proceed further. Let us consider any one of the parallelogram. Let us consider any one. Here I am considering the parallelogram BFED. We are considering BFED. We are considering this parallelogram, and you can consider any parallelogram according to your wish. And you can see here FD is a diagonal, right? And do you remember what we had learnt in our first class? The diagonal divides the parallelogram into 2 congruent triangles, right? And as FD is a diagonal, we can easily say these 2 triangles are congruent to each other. and you should be careful with the naming. BFD should be congruent to EDF, and it should be in the given order, right? Like B should exactly overlap on E, F will overlap on D, and D will overlap on F when the two triangles are separated out. And similarly, for other parallelograms where FE may be a diagonal or ED may be a diagonal, we get that from parallelogram. First, let us consider one of the parallelograms once more, AFDE, where FE is a diagonal. So we can see that FAE is congruent to EDF, right? And once more, let us see the diagonal ED now, or we are looking at the parallelogram DFEC. The diagonal DE divides this into two equal triangles, or DEC is congruent to triangle EDF, right? So we have got the center triangle, the triangle which is shown in white, is congruent to all the three triangles, right? And if a single triangle, triangle is congruent to all the other triangles, obviously all the triangles must be congruent to each other as well, right? Because the central triangle connects them all by the same rule of congruency. Hence, all the triangles are congruent to each other, right? All the triangles which are the smaller triangles, this one, this one, this one, and this one, all these are congruent to each other. And finally, we have proved that after joining the midpoints of the sides, of the corresponding sides, and after the entire triangle is divided into four equal parts, we can show easily that the four triangles are actually congruent to each other. So this is how we have solved. We have first used the midpoint theorem to find out which are the parallel sides, and using the parallel sides we have found out the respective parallelograms. And after we have found out the parallelograms, we have considered their diagonals so that we can find out two triangles divided by the diagonal are congruent to each other, right? And we have used this repeatedly 3 times to show that the central triangle is congruent to all the three triangles. And if the central triangle is congruent to all the triangles, then of course all the triangles must be congruent to each other as well, right? Because they are exactly overlapping onto each other. Thus we get the 4 triangles are congruent to each other. So let's move forward. But before moving forward, let us think something more about this figure. Let us find out what we can extract more from the given figure. Yes, we have of course solved this question, but for more knowledge, let us see what extra can we get from this given figure. We know that all the triangles are congruent to each other, right? So let us consider the 3 triangles which are congruent to each other. Triangle EDF, which is the central one, triangle DEC, this one, and triangle BFD, which is this one. Let us consider these 3 triangles. Let us consider these 3 triangles. So you can see FE must equals CD from this parallelogram, right? Because the opposite sides are equal and parallel. Also let us consider this parallelogram. FE must also be equal to DB, right? FE must also be equal to DB. So can you see one thing? If this sides measures something, the entire side BC measures twice of that. It is consisting of 2 equal parts, right? which measures the same as one part which is joining the midpoints. So you can see CD is equal to DB, right? CD is equal to DB. Why? Because D is the midpoint. And also CD plus DB is equal to BC, right? And from this we can get, we replace CD with FE and DB also with FE, because all these are equal as we have got here, right? So after replacing all the terms in FE and keeping the right hand side as BC, what we obtain is quite interesting. We obtain twice of FE is BC, and after simplifying, FE comes out to be half of BC, or this length FE must be half of BC. And this is true for any case, any triangle where the midpoints of two sides are joined, right? Or in other words, we can similarly show FD, this side FD is equal to half of side AC, right? And also ED, this one ED equals half the side of the corresponding base. So you can see, if we are joining the midpoints of two sides, obviously that line segment is parallel to the base, and also we have found out that the line segment measures half of the base, the corresponding base, right? So we are going to use this in the following question, which we are going to solve now. Let us use what we have learned from that figure in this question. Here we need to show that the line segments joining the midpoints of the opposite sides of a quadrilateral bisect each other. Let me repeat, the line segments joining the midpoints of the opposite sides. Midpoints of the opposite sides we need to join, and we need to show that these line segments which go crisscross way actually intersect at a point where so here we have to show that the line segments joining the midpoints of the opposite sides of a quadrilateral bisect each other, right? So we are going to use what we have learned from the earlier triangle, right? The line segment joining the midpoints of the triangle is parallel to the base, of course, and also half of the base, right? The line segment joining the midpoints is also half of the base, and we are going to use it in this question. So let us first draw the figure according to the given question. Let us join the midpoints. So we have drawn the midpoints here, E, F, G, H, the corresponding midpoints of the sides, and named them in an anti-clockwise manner as I had told you. And then we have joined them, and you can see the intersection point is at O. So we need to prove that EG and HF get bisected at O. So let us draw AC and HG, and you can see here that in triangle ABC, H and G are the midpoints, and the line segment HG is actually a line segment joining the midpoints, which must be parallel to AC, right? HG must be parallel to AC, and of course HG is also equal to half of AC, right? Because we have learned how this comes in our earlier slides. So we have got HG parallel to AC, and also HG equals half of AC. So let us keep this information aside because we will need it later, right? So let us look at one more figure. Let us look at the lower half, triangle DAC, and here E and F are the midpoints, and similarly EF is parallel to AC, and also EF is parallel to AC, and EF is half of AC, right? EF equals half of AC, and we are keeping this information also aside because we will need it later. And from the information we have obtained, can you see one thing? HG is parallel to AC and also EF is parallel to AC. So can't we say HG is parallel to EF? Of course. And also HG and EF both measure half of AC, right?
You are currently the only
So
person
HG
in this conference.
must be equal to EF also, right? So HG parallel to EF, also HG equal to EF. So let us consider the two triangles, triangle EOF, which is this one, and triangle GOH, which is this one. Let us consider these two triangles. So angle EOF, which is this one, and angle GOH, which is this one, both of them are equal as they are vertically opposite, right? These are vertically opposite angles. And EF equals HG, as I had told you, because both of them equals half of AC, or they are of the same length. And angle FEO, which is this angle, and angle HGO, which is this angle, both these angles are equal. And how is that? We are using HG parallel to EF. We are using HG parallel to EF, right? And HOF is the transversal. HOF is the transversal, and we are seeing GH and EF as the parallel sides. So this angle must be equal to this angle. Why? Because they are alternate angles, right? So you can see we have got three criteria: one angle, one side, and one more angle. So we can say, by naming them in the specific order, we can say triangle EOF, this triangle, is congruent to triangle GOH, this triangle, right? These two triangles are congruent to each other. And after this, very easily by CPCT we can tell OE equals OG, right? Because the corresponding parts must be equal. The OE part is equal to OG, or we can see O is lying at the midpoint of EG, right? So O has bisected EG. Now let us see whether O has bisected HF also or not. And very easily by CPCT we can say these two sides of these triangles are also equal. OF is equal to OH, and finally we have obtained O is also lying on the midpoint of FH, right? O is also lying at the midpoint of FH. So we can say O has bisected EG and also HF, or both the lines EG and HF have intersected at a point which bisects them. Or specifically, EG and HF get bisected, or they bisect each other at O, right? So we have proved, or we have shown what the question had asked. By joining the midpoints of the opposite sides of a quadrilateral, we actually see that they bisect each other, right? And here in the figure, the bisection point is O. So you have seen how we can easily use the midpoint theorem and how effectively we can use, and it actually simplifies our question. You can see in how short steps we have solved the question which involved a quadrilateral or which involved 4 midpoints, right? So in this class we have learned about the midpoint theorem, and we have actually talked about it a lot, and we have learned many things about the midpoint theorem. How we can say that the line joining the sides of the midpoints of the side is parallel to the base, and also half of the base. And see you next time.